Welcome to the fourth topic, annuities, perpetuities, and payments. We've been moving values in time, present value to future value, compounding, future value to present value, discounting. Up till now, we've had only two value variables, PV or P0 and FV or PN. We're now going to add a third value variable, the annuity. The annuity is a finite series, so a series that has a number of payments that is known. The payments are going to be equal and they need to be separated into equal time intervals. If we look at the illustration, you'll notice that the PV that's shown under the timeline, and we have 10 annuities or payments that are above the timeline. On the first diagram, the total of the payments is $129.51. So that total includes principal and interest. Notice that all of our payments are equal and they're completed at equal intervals. The second illustration, the one below, each of these payments discounted by the corresponding number of periods. The total of this present value is equal to $100. In other words, $100 repaid over a certain period of time, 10 periods here, at a rate of 5%. That will give me an equal payment of $12.95, 10 equal payments of $12.95. If I discount each of these payments, these are the values discounted by 1, 2, 3, 4, etc. number of periods. These are the present values. When I add them back together, they're equal to 100. In other words, our PV here is equal to the sum of all the future values when they're brought back into a PV. We'll come back to that concept. Through the presentation, we'll discuss both types of annuities, ordinary and annuity due. The difference between the two. An ordinary annuity, the payment is due at the end of the period. In other words, my P0 would be here at time 0. The payments start one period after, so on and so on. In the annuity due, P0 is also here at time 0, but we also get a corresponding payment right away. And all the other payments are spread over the period. The illustrations here show the payment at the beginning of each period and the impact on PV. Why? Because the payment number 1 is not discounted, making its PV bigger. So each present value is slightly higher than what we saw in the previous example, and you can notice the total of the annuity due. The payment is now lower, our grand total of all payments is lower, but the present value is equal. On your calculator, annuities by default are at the end of periods. In order to change the annuities to the beginning of periods, you need to hit the BGN end toggle switch to toggle between both modes. As mentioned before, annuities can be discounted. They could be compounded. Or a PV can be transformed into annuities or payments. To calculate the PV of annuity, you need to discount each of the annuity by R% and by the corresponding end period and total all of the PVs. This is the equation that does it in one operation. You'll notice we have a new variable now, C, which is the annuity. So if we look at an example, the present value, 5 annual payments of $1,000, the interest rate 5% per year. The same rule stands. Units that are associated to R cannot be changed. So if my 5% is per year, my N has to be a number of years. So PV is going to be equal to C, 1,000, multiplied by 1 minus 1 plus I, so 5%, raised to minus N, 5 years, divided by the interest rate again. All this will give you $4,329.48. So that's the present value of this annuity. For the annuity due, the equation differs. Note, since the payments are done at the beginning of each period, it's like if you were doing the payment at the end of the previous period. So those two time periods, the end of one period and the beginning of the next, kind of correspond. There's like a blink of an eye between the two of them. So we could say that a beginning of period is equal to the end of the previous period. That will explain here the n plus 1. Since payment number 1 is not being discounted, it's just added in completely, that will explain the second 1 plus that we have here. So an example, still the same thing, $1,000 placed for 5 years at a rate of 5%. So the same example, a payment of $1,000 each period for 5 years at a rate of 5% will give me a present value of 1,000 times 1 plus times 1 minus 1 plus the I, n minus 1. So we had 5 years, 5 minus 1 is 4, divided by 0.05. This whole calculation will give me $4,545.45. On your calculator, ordinary annuity. Again, we're just going to enter the amounts into our calculator. If you've been using your calculator before, just to make sure all of our memories are empty, we're going to hit the second CA button to make sure that all of our memories are empty. Then we're going to enter the variables. 5 is my N, 5 annual payments. Y is 5. My payment, 1,000. Future value, we're going to enter 0 because we have no future value in here. We're going to compute present value to have $4,329.48. Notice the negative sign. Just like in our previous exercises in the previous video, I told you when we're going to enter numbers that are above our timeline, we're going to enter them as positive numbers. My payment here is a positive number. The calculator will generate a negative PV because that one is under the timeline. So a present value of $4,329.48. The table here illustrates the underlying schedule. Notice that each annuity is composed of part interest and part amortization of the principal. The annuity is always equal over all the periods, but is composed of a different interest and a different principal amount for each payment. For an annuity due, we'll hit the second and CA to clear all of our memories. In order to do begin, we need to toggle into the begin mode. So hit the second button and begin \n. That's the same button that's used for future value. Now we're just transforming into end of periods. Notice that on the screen will be displayed BGM on the upper left hand of your screen. That tells you that your calculator now is in beginning of period mode. We'll enter our variables again. 5 in N, 5 in Y, 1,000 in payment, and we'll compute our present value to get the answer, $4,545.95. Again, the table illustrates the amortization of the principal over the period. Notice the interest for period 1. It's not a mistake. Since our payment is done at the beginning of the period, our principal has not accumulated any interest at this point. So our principal is decreased by $1,000 right away. In order to calculate future values of the annuities, We're going to do the inverse from what we did earlier. So we need to calculate a future value for each of the payments at the corresponding number of periods with the rate of R, and we'll just total up each of these values. The equation shows how to get there in one simple operation. For example, my 5 annual payments of $1,000, interest rate 5%. We're going to transfer that into a future value. So we're going to take 1,000, our C, multiplied by 1 plus the percentage, 5%, raised to the power of 5, our N, minus 1, all that divided by the interest rate, 5. Gives me a grand total of $5,525.64. So if you were to place $1,000 each year for 5 years and the interest rate was 5%, at the end you will not have $5,000. You'll have $5,525.64. The future value of an annuity due, again because of the periods, we're going to add in 1 on the N, because all of our payments now are done at the beginning of the period. So by the end of the 5th year, we'll have 1 additional period in there. So the future value, $1,000, multiplied by 1.05, raised to the power of N plus 1, 5 plus 1, 6. Minus 1. All of that divided by I, interest rate 5%, to which we resubtract 1, gives us $5,801.91. So using the calculator, again, let's clear our memory. Second CA, make sure you're not in beginning mode, toggle that back to end, and we'll enter the variables. 5%, 5 years, $1,000. 5%, 5 years, 1,000 in payment. Let's compute future value. Notice I've entered my payments in positive. It generates a negative future value. It's just, again, the convention of how the calculator works. Again, second CA, to clear our memory, we'll try an example with the annuity due. Remember to toggle back into beginning mode, second, BGN. We'll re-enter the variables 5, 1,000. Payment, and compute the future value. And we'll obtain the value, future value, 5,801, which is a bit higher than what we obtained using the ordinary annuity. To compute the payment, or the C variable, you'll need to isolate C. Now the equations here illustrate this conversion. So if we complete this example, a loan of $2,500 amortized over 7 years at a rate of 7.5% interest. We'll follow our equations and we replace our variables. We'll obtain 2,500 divided by 1 less 1 plus the interest rate raised to the power minus n, and this whole, all of this in brackets, multiplied by 0.075. That'll give me $472. For the annuity due, the same thing, 2,500 divided by 1 plus, in brackets, 1 minus 1 plus I, our rate, multiplied by minus our n minus 1. So if we had 7 years, we now have 6. All of this divided by 0.05 is the divider for the annuity due, which gives me $439.07. On the calculator, again, very simple. All we have to do is enter our variables and calculate the remaining. Make sure that your memories are empty. Make sure that you are in N mode to start with. 7 periods, 7.5, 7.5 in Y. 2,500 is our PV. We're going to enter that as a negative number and compute the payment. $472. Now let's try this. Our memories have all been stored. Let's just hit the second begin button, compute the payment. You should obtain now $439.07. So the right answers are already computed. You know that you can always use the same values for the variables that are already stored into the memories. Two special cases of annuities. The first one, a perpetuity. So we'd like to calculate the present value of this annuity, C, that's going to be perpetual, never ending. N is going to become infinity, and C, our payment needs to be fixed over time. For example, this could apply to dividend income. If a dividend is fixed and is going to be obtained over and over, perpetual, this would be a good formula to use. So since 1 minus 1 plus I raised to minus infinity, that becomes 1. So since that is 1, C multiplied by 1 divided by I becomes C divided by I. So if you have a perpetual payment, you could transfer this into C divided by I. So as an example, our corporation here is issuing a security. It's going to pay $5 return each quarter perpetually. Investors are expecting a return of 8% compounded quarterly on their money. So 8% is an annual rate. We're going to have to divide that by 4 because there are 4 quarters in the year. So they're expecting 2% per quarter return on their income. So $5 divided by 0.02 gives me $250. Let's try an example, the same example, using the calculator. We're going to enter 999 in N. That's close enough to perpetuity for our example. So we're going to enter the variables N, 999, Y, 2, PMT, 5, and compute the present value. You should obtain 250. Another case where we have perpetuities, but with a growing rate. In other words, C is going to grow at a constant fixed rate for each period. In order to account for that, since C is static in our equation, we must review I. So C divided by I minus G, G being the fixed growth rate, will give us the present value. In both perpetuity cases, if payments are done at the beginning of the period, you need to add plus C to the equations in order to add the non-discounted payment received at time 0. This is it for annuities, perpetuities, and payments. Now, go have a look at Spreadsheet Solutions, the video, in order to learn how to use Excel to do these calculations.